Oh, you finally made it. You're late to class, you know. Math class is very, very important. What could you have been doing that was so important that you had to miss math class? Or you were relaxing and sleeping? Oh, I can't believe it. Math, some might say, is about relaxing and sleeping, but I say is about education. You know what? I'm going to prove that to you today. I think that our lesson will be full of proofs. Strictly mathematical proofs. And then maybe you can give me a mathematical proof that math can help you relax and sleep as well. I was actually just getting started on a little proof here. It's actually a proof of the Quadratic Theorem. I hope you're familiar with the Quadratic Theorem. Well, I guess I'll go over the Quadratic Theorem first. This is the first line of the proof, but the Quadratic Theorem states that the solution to any quadratic equation, this being a quadratic formula, or quadratic equation, and the solutions to this, meaning any occurrences when the answer to this is 0, hence the 0 there, so the solution to this equation, ax squared plus bx plus c equals 0, where a, b, and c are constants and x is our independent variable, equals 0. The solution is x is equal to negative b plus minus root b squared minus 4ac minus 4ac, all of that over 2a. So this is what we're going to prove, and this here is the beginning of the proof. So why don't we just erase this, and now that we know our goal, we'll get started. This is a strictly algebraic proof, and once we've done this algebraic proof, we'll move on to proof by induction, proof by contradiction, and if we'll have time, we'll see if we can get to one more fun proof, maybe a geometric proof, such as maybe Pythagorean theorem. We'll see what we have time for, though. So this is the first line of the proof, and how we start is we'll actually divide all of this by a to give us x squared plus b over ax plus c over a is equal to 0. And we can actually move this c over a to that side to give us x squared plus b over ax is equal to negative c over a. Now this is sort of where it gets tricky, and this is where a lot of people would actually give up or get lost, but today here I'm going to show you that it's not really that difficult, and I'll give you a big hint here. What does this side start to look like? It sort of almost looks like it could be a perfect square, in fact. We have this x squared term here with no coefficient, and a b over a x term. So we're just missing this final constant term here, and we're going to see if we can complete that square. And in fact, the values are x squared over b, or x squared plus b over ax, and this final constant term is actually b squared over 4a. And since we add that to this side, we have to add it to the right side, plus b squared over 4a. Sorry, this is actually 4a squared. This should be a squared. And what's very interesting to note here is actually b squared over 4a squared. This is actually the same as b over 2a, all squared. So this and this are actually equivalent still. And we can continue this proof by taking this left side and actually turning it into that perfect square. So we get x plus b over a all squared. And this is equal to negative c over a plus b squared over 4a, but we can actually change it, so we can add 4c up here, 4a down here, and multiply this by an a, so we get 4a squared, b squared over 4a squared. So now we have common denominators on this side, so we can actually add these together here. So this is actually equal to b squared plus 4ac over 4a squared. I did some rearranging here. I moved the b squared out front, swapped a and c, but because of distributivity of multiplication and commutativity of addition, the basic properties, we are actually allowed to do this maneuver. So are you following everything so far? Does this all make sense to you so far? You can sort of see that we're really starting to shape up to our target, and our target is actually, I'll write it down again here, so x is equal to negative b plus minus the square root of b squared minus 4ac over 2a. I apologize for my poor handwriting, but I'm sure you understand what this is saying, correct? So, yes, we have, this is our target, and you can see how we're starting to shape up what's going on in here. So the next step here is to actually take the square root, x plus b over a, of both sides. When we take the square root of the side with the square, we drop the square, and when we take the square root of this side, we'll end up with this big square root over the whole value, b squared plus 4ac over 4a squared. And we can distribute this square root. We can actually distribute this between the numerator and the denominator independently. So we end up with a b squared plus 4ac in the numerator and 2a in the denominator. As we can take the square root of just the denominator to get 2a. I hope you're still following. And finally, this final step is we just subtract ba from the other side, from both sides. So we subtract b over a from this side. We subtract b over a from this side. So we get negative b over a, negative b over a. I see. I actually made a critical error here. Very foolish of me. Is that actually when we did this b over 2a, for some reason I did not continue this 2a onwards, but we already took the square root, so there's no reason to drop that 2a, because in fact 2 times b over 2a gives us that b over a that we want, and that's a property of the perfect square expansion. So all of this is actually 2a, and we subtract b over 2a plus this value here, b squared plus 4ac over 2a to give us our final desired answer. X is equal to negative b. Another foolish mistake. Oh my goodness, I'm just full of mistakes today. This is what happens when you show up late. Is my brain is already gone. It's already gone. You need to show up on time if you want the prime Assan tutor. You know, it's really, really unfortunate that you made me miss my prime. Maybe we'll do a proof on prime numbers. That'd be fun. But yes, when we took these square root, you have to do plus minus, because when you square a number, negative 2 is 4, negative 2 squared is 4, 2 squared is 4. So when you take a square root, you don't know if the original was positive or negative, hence plus minus. And this here, so this is equal to plus minus. This here is plus minus to give us our negative b, plus minus root b squared plus 4ac over 2a. And this here is exactly what we're looking to get from up here. And we can end with our final QED box. So our proof is complete. Now, are there any questions about the proof of the quadratic theorem? No? Complete understanding? No questions? You really are quite a genius sometime. Really, truly. I forget sometimes. Maybe it's all that sleeping and relaxing. Huh. Okay, well, we'll move on to the next proof now. I'll just clear off the board here. Just go shoop, 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 shoop. Very good. Now we're ready for our next proof here. Okay. Well, I think for our next proof, we will do a very simple proof, but an excellent proof to demonstrate what a proof by induction is in math. Now, induction is a very, very powerful proof method in mathematics. It's used widely. It's been used for many, many theorems, and today we'll just do a little introduction to proof by inductions using a simple example. The idea behind a proof by induction is actually that if you can solve it for sort of simpler cases, then adding on one more layer of complexity doesn't add that might be easier to prove by just adding one layer at a time. So if you can prove it for the base case, and we'll get into what that means in a second, then it might be a lot easier to prove for the next cases. And the best way to understand this is to give you an example. I'm actually just going to change my pen color though, because that's boring. We need something more fun for induction. Induction is so fun. Induction is so fun. Induction. Induction is so fun. Okay. Alrighty, so what we're going to be proving with induction is the property that SK, here, I'll write it over here, S, so suppose that K is an integer, so let K be an element, actually, no. K will be a natural number, so let K be an element of the naturals. Then S of K is equal to K times K plus 1 over 2, where SK is the sum from 1 to K. So the sum from I equals 1 to K of I. But we're not going to be proving it algebraically. We could do a proof directly from here to here using some simple expansions. But no, we want to demonstrate an inductive proof. And so we'll do an inductive proof of this property. So remember I mentioned that base case. That's really important. So the base case, when your domain is natural numbers, is 1, because 1 is the first natural number. So we'll start base case for K equals 1, S of 1 is equal to 1 times 1 plus 1 over 2, which is equal to 1 times 2 over 2 is 1. Good, and that is equal to the sum from I equals 1 to 1 y, which is just equal to 1. So, yes, base case is proven. Base case true. Our base case is true. Wonderful. And that is the basis of a proof by induction. The basis of a proof by induction is base case. The next up is our inductive hypothesis. So now we assume inductive hypothesis. Assume for some K greater than 1, that the property holds for s of k minus 1. So we'll say s of k minus 1 is equal to k minus 1 times k over 2. So assume that this is true. Now our inductive step is the next step. So we have multiple steps. So the first step is prove the base case, state your inductive hypothesis. Now we need to do the inductive step. So we assume that this is true. Then what is sk? Well, the sk is the sum of all natural numbers up to k is the sum of all natural numbers up to k minus 1 plus k. I hope that makes sense. So just as an example, the sum of all numbers up to 5 is 1 plus 2 plus 3 plus 4, which is the sum of all natural numbers up to 4 plus 5. And this whole thing is s of 5. Does that make sense? Yes? Okay, good. So now we can move on. You know, you're really picking things up so well today. I'm very proud of you. Good job. Good job. Very good job. So inductive step is sk is equal to s of k minus 1 plus k. Now, we already know that s of k minus 1 is equal to k minus, k minus 1 times k over 2 by our inductive step. So by our inductive hypothesis. By our inductive hypothesis, this is true, plus k, which is equal to k minus 1 times k over 2 plus 2k over k, or over 2, which allows us to equate this to k minus 1 times k plus 2k all over 2, and we can factor out a k to get k, times k minus 1 plus 2 over 2, which is in fact equal to k times k plus 1 over 2, which is our goal. That's our theorem. So we've now done it, and QED. The reason we're allowed to make that jump, by the way, the reason we're allowed to make this assumption with our inductive hypothesis is because the base case is true. So we proved it for s of 1. So now by our inductive step, s of 2 is true. And because s of 1 is true, this implies s of 2 is true. But s of 2 being true implies s of 3 holds, which implies s of 4 holds, etc., etc. And that is the basis of a proof by induction. Now, there's actually also strong induction, where you need to assume not only s of k minus 1 here, but you need to assume s of 1 up to sk minus 1, or any number of properties holding. So in those cases, you have to prove as many base cases as are needed to satisfy your base requirements. And that's how you would use the principles of strong induction. A very, very fun proof technique, very common in the workplace. But now we will erase this up. Boop, 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 boop. You're following me still, right? You're still following? Oh, okay, good. Good. Brush. And erase. Erase. Okay. I think we're ready for our next proof. Okay. So we'll move on to our next proof now. And a new color again, because we must. It really is necessary. Okay. The next proof that we are going to look into is a proof by contradiction. Again, we're going to do a very, very simple proof just to actually prove it. Just to show how a proof by contradiction works. With a very simple proof, we'll be proving that no integers, so no we'll write this in mathematical terms. There does not exist x, y in the integers such that 24x plus 12y equals 1. Okay? Does this make sense so far? This is what we're going to prove. And we'll do it by contradiction. So how a proof by contradiction works is you assume that the hypothesis is, you assume the opposite of this conditions and show that it leads to a breaking of a fundamental principle of mathematics or another proved theorem. So we would say, suppose for contradiction that there exists x, y in the integers such that 24x plus 12y equals 1. So then what we can do is we can divide all terms here by 12. 2x plus y equals 1/12. And, well, there's our contradiction. Since 2x is an integer, y is an integer, and the sum of two integers, is an integer, and 1/12 is not an integer, we've reached a contradiction. Contradiction. We reach a contradiction. Thus, this initial statement is true, holds, and that is the end of our proof. Again, very, very simple proof, and yet this proof by contradiction is a very, very powerful proof where if you needed to prove something is true, but there are many, many cases you might need to check, you can do a proof by contradiction, and it actually might boil down to a very simple thing, like right here. Right here, it boils down to something very simple, that this is impossible. And obviously, in this case, it's very easy to see that that's not true, the initial statement at hand, but in other cases where you might need a proof of contradiction, it can become a lot more complicated. A lot more complicated. So that is our proof by contradiction. We will erase. Erase it all. It's all in your brain, right? It's all in your head. You picked it all up. You picked it all up. I hope so. I hope you picked it all up because you're going to be tested on it at the end of this session. I hope you're ready. Okay. Well, I think we have time for one more proof. I think we have time for one more proof. The final one. We'll do a very fun one. It's a little bit geometric. It is the proof of Pythagorean theorem. And to start off, I'm just going to draw a little diagram. This is a square with sides, side length of A, so we'll say capital A, but we're going to denote this capital A to be equal to little a plus little b. So we have A, B, and the barrier between A and B is an inner square. But what you'll notice, oh, that was really poorly drawn. This is a square, not a diamond. Okay, it's a little bit better. This is a very bad diagram. It's not to scale, but in reality, this is a square inside with side length C, 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 C. So we have AB, 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 A, B, A. Now, we know that the area of this outer triangle, I'm going to say triangle 1. We're going to call the outer triangle is triangle 1. Okay, this purple isn't really working. I'm switching colors. And then let's see, we'll go to orange. So this outer triangle is triangle 1. There's this outer triangle, and the inner triangle is triangle 2. Point at the inner triangle, and the area of triangle 1, I'm going to denote an area function by capital A. So area of triangle 1 is equal to A plus B squared. The area of triangle 2 is equal to C squared. Now what does that mean? This now means that the area of these region plus this region plus this region plus this region is equal to the area of the outer square minus the inner square. So we end up with 4 times, these are all right triangles, obviously, right angles, meaning that if A is the length of the triangle, then B is the height. So we have 4 times A, B over 2. And that's just the definition of the area of a triangle. It's, width times height over 2. So those 4 regions is equal to our area of triangle 1 minus our area of triangle 2. A plus B squared minus C squared. Okay, so here we go. So now we can start simplifying this. This cancels out to be 2, so we get 2. AB is equal to A squared plus B squared plus 2AB. And that's the expansion of this, minus C squared. So now we can move this C squared over here, and this 2 will be over here to get C squared is equal to A squared plus B squared. Or A squared plus C squared equals, A squared plus B squared equals C squared, which is Pythagorean theorem. There we go. That's about proof sign. So we've done it. We have proved Pythagoras' theorem. Well, you have just done wonderfully, really wonderfully with this math, with these proofs. I mean, I truly, after you came late and all, I was not expecting you to do so well. I'm really quite impressed. You really impressed me. So we ran out of time, so there's not going to be any tests today. But next time, you better be ready, because I'm not going to be helping. You're going to have to do it all. Anyways, well, thank you for coming. I hope that you found that the math helped you with your sleep and relaxation, and I hope that your sleep and relaxation helped you really focus on the math and absorb these proofs and these proof concepts. We got to see proofs ranging from algebraic proofs to proof by induction to proof by contradiction to a geometric proof, really all fundamental proof concepts in mathematics, and I hope that you really enjoyed this experience. Yeah, have a great day.